This session is Breaking Samsung's ARM TrustZone with Maxime, Peterlin.
It should be. It works? All right. Let's go. All right, good afternoon, everyone. Thanks for coming to this presentation about breaking Samsung ARM TrustZone. My name is Maxime Peterlin. I'm working at Quarkslab, which is a French security company. And I've been working on this subject for about a year with two of my colleagues, Alexandre Adamski and Joffrey Guilbon. So our agenda for the day is the following. First, I'll talk about the current state of embedded security to give you an idea of where TrustZone is coming from and why do we need it. Then I'll introduce the actual ARM TrustZone technology, give you an idea of what the internals are. Then I'll focus on Samsung's TrustZone implementation, and after that we'll talk about vulnerability research, tool developments, and exploitation. So let's start with the current state of embedded security. So a long time ago, we used to have this traditional architecture with everything inside the kernel. So we had secrets, we had security mitigations, etc. And they did that because they thought that, well, the kernel is really hard to break into. So just let's put everything in there. But as it has been shown time and time again, the kernel is not unbreakable. And if you're able to compromise it, then you have access to your entire system. So at this point, we can ask ourselves, how do we protect ourselves if the kernel is corrupted during the boot process? Well, during the boot process, what we can do is implement mechanisms such as secure boots. But if we try to protect our system against runtime compromission, well, it's a little bit more complicated. What you could do is to use an hypervisor. Now, instead of having your security inside your operating system, it's now in the hypervisor. And now you're looking over your virtual machines to make sure that there's no compromission. But the issue is that it's still software implemented. If you have a VM escape or an hypervisor compromission, you still have the same issue as before, and your entire system is compromised. At this point, vendors realize that software is not enough because you can make mistakes when implementing software. And they realized, they said that maybe we can leverage the hardware to enhance the system, the security of the system, and act as some kind of safety nets. And this is where trusted execution environments came from. So with trusted execution environments, what's going to happen is instead of having a single state in which your CPU is running, you're going to have two. One is the non-secure state. So this is like the regular state where you regular non-sensitive operations will be performed. And then you're going to have a secure state where all the sensitive operations will be performed. And what's going to happen is that even if you have a compromission in non-secure state, you won't be able to access the secure state because the hardware will prevent it. So we can have a different type of implementation of trusted execution environments. So the first one I'm going to talk about is the virtual processor. So this is what is going to be used by our ARM TrustZone. In that implementation, you have a CPU, and you have your system on chip with all the peripherals, the hardware resources, and you can separate these resources into the two states I was talking about. Then you can also have a non-SOC processor. This is pretty much what is used by Apple in their secure enclave, at least according to their documentation. And now, instead of having a CPU that can run in two states, you have two CPU, and one dedicated to non-sensitive operation, so in non-secure state, and one running in the secure state. And finally, you can have an external coprocessor with just a regular system on chip that is running in non-secure state. And next to that, you have a secure coprocessor that is going to be dedicated to all the sensitive operations. All right, so now let's talk about the actual ARM TrustZone technology. So ARM TrustZone is a system-wide hardware isolation mechanism, meaning that it's going to be based on two layers. So you have your hardware architecture. So this is where all the partitioning is going to take place. This is where you're going to have your data bus, your control bus, that is going to be separated into non-secure state and secure state. And you also have your software architecture, where you have the actual software implementation that you're going to run in secure state. So at this point, I've only talked about non-secure state and secure state. What you usually will encounter are actually secure and non-secure worlds. And again, so in the secure world, you have all the trusted code, you have all the sensitive operations that are being performed. And in the normal world, this is where you will have, for example, on Samsung's devices, this is where Android is running. You have your normal world that is considered as compromised by design. And this is where all the non-sensitive operations take place. So to know, so the secure or non-secure state of the CPU is going to be determined by the least significant bit in the secure configuration register. And so this least significant bit is called the NS bit. And it's going to be clear when you're running in secure state, and it's going to be set when running in non-secure state. Just a quick reminder on the privileges separation that exists on ARM system. So in ARM v7, you have what is called privilege levels, and in ARM v8, you have what is called exception levels. So this is just a naming convention. It's pretty much the same thing. And from now on, I'll only talk about exception levels. So in EL0, so exception level 0, you have all the applications. So in the normal world and in the secure world, so just the least privileged exception level. Then you have EL1, this is where the operating system will be. Then EL2, your hypervisor, and then EL3. EL3 only exists in the secure world. There's no EL3 in the normal world. And this is where you will find your secure monitor. I'll talk about the secure monitor just after. One thing I wanted to note here is that, as you can see, there is no hypervisor in the secure world. This is because at the moment there is no way. ARM does not provide any way to do that in the secure world currently. And this is an upcoming feature that is coming ARM v8.4 with the addition of secure partitions. But for the moment, what you have is a privileged escalation by design, meaning that if you have code execution in SEL1, you have access to the same resources as EL3. All right, so now, now we know how we can communicate. We can switch between the two states, or how we know how we can be if we are in normal world or in secure world. Now, how do we do to communicate between these two worlds? So to do that, we are going to use the secure monitor, and the secure monitor is going to run at the highest ARM exception level on an ARM platform. And if you want to exchange data between the normal world and the secure world, you have different mechanisms to do so. First, we have explicit calls. So these are secure monitor call instruction. Then you have also interruptions, external aborts. And if you are in the secure world, and at least in SEL1, you can directly write into the pstate register in ARM v8 or the CPSR register in ARM v7. Because it requires certain privilege to do so. All right, so now let's talk about the different software implementation that you can find in the secure world. So in the secure world, you can have a full-fledged operating system running, so with a secure OS that is going to load trusted applications. And this is pretty much what you're going to find on Samsung's devices, on Qualcomm's devices. Then you can have a lighter solution, pretty much completely the opposite, where you have a synchronous library, which is going to be used by the normal world as some kind of secure API. And you can run cryptographic operations, and you have all your secret keys that are stored in the secure world, and the normal world cannot access them. And this is a way that you can do cryptography in a secure manner. And an example of such an implementation will be the Nintendo Switch. And finally, the ARM documentation talks about intermediate options. We have never seen something like this in practice, but in theory, because the TrustZone technology is so flexible, you can do pretty much anything you want. But to our knowledge, it's not used that much. All right, so what is TrustZone actually used for? Well, most of the time, TrustZone will be used to access hardware-backed features. For example, the cryptographic engine, credential storage, the TRNG, etc. And using these hardware-backed features, you can start to create more advanced systems, such as DRMs. And you can also do things such as protecting and monitoring the normal world by using the secure world. And an example of that would be Samsung's RKP for real-time kernel protection and Samsung's PKM for periodic kernel measurements. All right, so now I've talked about the ARM TrustZone, explain a little bit how it works. And now let's see how the implementation that has been done by Samsung. So Samsung devices are a bit particular because they can either have a system on chip that is made by Samsung, so this is the Exynos SoCs, and then they can also use Qualcomm's Snapdragon. The reason for that is that depending on the country, because of telecommunication norms, because of patent issues, you will have either an Exynos or a Snapdragon. The thing that is important here is to note is that Samsung's TrustZone is only found on Exynos SoCs. Otherwise, it's going to be Qualcomm's TrustZone. And this TrustZone was first used on the Samsung Galaxy S3, and the trusted OS that are used, there are two different trusted OS. The first one is KiniBee, that is developed by Trustonic, and you can find this trusted OS from the Galaxy S3 to the Galaxy S9. And now they are starting to replace KiniBee by their own implementation, which is called Tigris, and you can find this one on the Galaxy S10. And so I'm only talking about Galaxy models here, but these two trusted OS are used on other phones and other models too. And this talk will focus exclusively on KiniBee. All right, so this presentation is not the first publication on the subject. There has already been research done on the subject before. So here I've noted three notable examples. The first one is reverse engineering Samsung S6 S boots by Fernand Song. In this article, he explains how the ARM trusted firmware, the secure monitor implementation that is used by Samsung works. And he also explained how you can extract the trusted OS from an OTA. Then you have Unbox Your Phone by Daniel Komarami, where he reverse engineered a really big part of KiniBee and the different components. A lot of our work is based on what he has done. And in his article series, he also explained how he exploited vulnerabilities in some trustlets. And finally, there is Trust Issues Exploiting TrustZone Teas by Gal Banyamini. And in this article, he has done a security analysis of different trusted execution environments. And one of the really important results that he has found is that there was no revocation in Samsung's TrustZone. And what that means is that if you have a trusted application that is vulnerable, you are still able to load it on the newest versions of the trusted OS, which should not happen because if you have a vulnerability, you patched it, you shouldn't be able to load all the trustlets in the newer TrustZone. And now KiniBee has implemented a feature that manages just that. But the issue is that at the moment, there are some trustlets that do not use that feature, meaning that even on the Galaxy S9, you still have revocation problems. And if you have a vulnerability in a trustlet from, I don't know, 6 months ago, you're still able to exploit it in upstream versions. Okay, so now let's talk about the architecture of Samsung's TrustZone. So in the normal world, you will have different components. So you have drivers, daemons, libraries, interfaces that are going to be used by the normal world to communicate with the secure world. The communications are going to pass through the SMCs. And since SMCs cannot pass a lot of information, what's going to happen is that we're going to use the SMCs to set up a shared memory buffer. And most of the data will be transferred using this shared memory buffer. Then you have the secure monitor implementation. So as I said, they are using ARM trusted firmware, which is an open source reference provided by ARM. And What is interesting with this implementation is that, yeah, first it's open source, so there are chances that it has been heavily reviewed, and it's pretty safe to use it, and also that it's really modular, meaning that any vendor can take this implementation and adapt it to their own needs. And finally, now I'm going to concentrate on the SEL0 and SEL1 components. And I'm going to call that the Trusted OS. And the Trusted OS is based on a microkernel architecture. So the Trusted OS is KDB. It's a 32-bit OS that is developed by TrustZone. And the actual microkernel is called MTK. And it's the only component that is going to run in SEL1. All the other components are running in SEL0, which limits a lot the attack surface that you have on KDB. But lesser privileged processes still need to execute some privileged operation. And to do that, MTK provides syscall. So with syscall, you can do things such as memory mapping, process creation, SMCs, but these SVCs are not available to all type of processes. It depends on their privileges, because they have software-defined privileges in SEL0. One of the other things KDB is responsible for is to build other components, and especially RTM. RTM is the runtime manager. This is also a component that is running SEL0, and this is like a special type of trusted application, and it's equivalent to the init process on Linux. Its main task is going to be to start and manage other processes, but also to manage the communication between trusted applications and the normal world, and also to manage the communications between all the processes running in SEL0. And to do that, so you have IPCs and also the Mobicore communication interface to communicate with the normal world. Then we have the MClib. So this is KDB's standard library. It's going to provide standard function for trusted applications, secret drivers, and also RTM. It's separated into two sets of APIs. You have the APIs for trusted application, which is called the TL APIs. And then you have the functions for used by secret drivers, which are called the DR APIs. And this library is especially useful when we're doing exploitation, because this is where we're going to find most of our gadgets. All right, so at this point, I've talked a lot about trusted applications, but I didn't give an actual definition of it. So trusted applications are like the equivalent of regular applications that you find in the normal world. And they're going to run in SEL0. And since your operating system running the Trusted OS has limited functionalities, what is going to happen is that you have your trusted applications that are used as an extension of the Trusted OS, so that you're able to implement more functionalities, such as Trusted UI, DRM, secret storage, etc. And these binaries, so they are executables, they are going to be loaded directly from the normal world. And to make sure that you cannot just load any executable, they are signed by TrustZone. So the life cycle of trusted applications. When you're going to load a trusted application from the normal world, you use the API in the normal world, you send your application in the secure world, the Trusted OS, RTM is going to check the signature to make sure that it's okay. Then it's going to make different checks and initialization, such as stack initialization. And one thing to note also is that the communication between the normal world and the trustlets will be mostly made using the world share memory buffer. And in KDB's TrustZone terminology, this world share memory buffer is called a TCI buffer. And this TCI buffer is going to contain data. So what's going to happen is that in the normal world, you're going to put data in your TCI buffer. You send a notification to the trustlet that data are waiting to be processed. The trustlet has entered an infinite loop where it's going to wait for this notification. Then it's going to look at the data that is in the TCI buffer. Depending on the data that you have sent, it's going to execute a certain type of command. And once this command has been performed, the trusted application write back the results into the TCI buffer, and it's going to notify the normal world that the command has been handled, and the normal world can now retrieve the results from the TCI buffer. Also, secure drivers. So secure drivers are a special type of trusted applications. They also run at SEL0, but they have more privileges than trusted, because they have access to a richer set of APIs, they have access to more SVCs, and they're also used by trustlets as an interface to access physical memory and also secure resources. So, and to do that, because we don't want trusted to be able to do anything, even though we are running in the trusted world, even though we're running in the trusted world, they are not completely trusted, and they cannot do anything they want. And the secure drivers are acting as some kind of secure buffer between the hardware resources and the trusted application. And so, in order to communicate with the secure driver, the trustlet will use IPCs and send data using that. All right, so this was a big overview of what the Samsung's TrustZone is and how it works. So now let's see how we are going to find vulnerabilities on this platform. So first, we needed to assess the attack surface on this target. So we are in the normal world, and we want to have a privilege to have code execution in SEL1 or EL3. What we can do is that we start by attacking a trusted application. Then we attack a driver, a secure driver. And from there, we have access to enough syscall to have a large attack surface on the trusted OS, on KDB. And here we could, find vulnerabilities in the SVCs and try to gain code execution in SEL1. What we can also do, because secure drivers are able to do SMCs, we could also attack the monitor from SEL0. This is also possible from the normal world, but the issue is that the attack surface is really small compared to the one that you have from the secure world. And also another issue is that because ATF is open source, there are chances that it has been heavily reviewed, and so it seemed kind of hard to find vulnerability in that. So we prefer to concentrate on trusted applications because they look like low-hanging fruits. So now I'm going to explain our journey in 5 steps. So the first one is, so now we want to attack, we want to find vulnerabilities in trusted application. So the first thing we need to do is to load them into a disassembler. So trusted applications are based on the MCLF format. It's the same thing for secure drivers and RTM. And this is a proprietary file format that is quite simple. And there was already an idle loader for that format, and we have also developed one for Ghidra. So these 2 loaders are available online if you need them. The next step was to identify functions in the trustlets, because in the trustlets you will have call to the mclib. And in the mclib, you have different functions that are reused in trustlets. And having access to this information is really useful because you get a general idea of what the trustlet is used for. And here we have an example of our script in execution. On the left, we have no symbol. It's pretty complicated to understand what's going on. But afterwards, after our script has been executed, we are able to have the name of the function and also its prototype. Okay, so at this point, we were able to do a static analysis, but what we wanted to have are dynamic capabilities. But since we have not access to the SDK of Trustonic, we needed to find another solution. So what we did is that we developed an emulator to emulate the trustlets. So it's a simple emulator that is based on Unicorn, and it's going to load the MCLF binary, it's going to map the shared memory buffer, and it's going to hook the MCLib functions and also implement some of them so that the trustlet executes almost completely. So here's an example of the emulator running. So the first thing I'm doing here is to create an input of the TCI buffer. So I'm putting this one in input.bin. And then I'm passing this input.bin to our emulator. And now the emulator is going to execute. And here we can see that the binary has been loaded. We have the different sections that have been mapped. And here we have, for example, the TL API log v printf function that has been hooked. And we can see the output right here. So the emulator is really useful during reverse engineering, but also during exploitation, because we were able to test our exploits on this emulator. So now we are able to find, so we have all the capabilities that we wanted. We are able to find vulnerabilities statically, but we also wanted to find them dynamically using a fuzzer. So this fuzzer is based on our previous emulator. If you're familiar with AFL Unicorn, we have an internal version of that is equivalent, but the performances are a little bit better. And we have used that so we have plugged this AFL fuzzer, AFL Unicorn-like project into our emulator, and we are able to fuzz trustlets using that. So here's an example. Here I'm running the trustlets. I'm running the fuzzer on the trustlets, and you can see that after only 12 seconds, we have already 3 unique crashes. So this is pretty useful. We have found a lot of vulnerabilities using that. Another way to find vulnerabilities that we have implemented is to use symbolic execution. And we have used Manticore by trust of bits. So the strategy that we have used is pretty simple. We are using, we are taking the TCI buffer, we are marking it as symbolic. Then we explore the different paths of the trustlet, so the different command handler, etc. Then we check the reads and writes to memory, and we look and we try to detect if there is an invalid address that has been accessed. So here's an example right here. I'm running the Manticore on the trustlets, and here you have a crash results. And right here you have R1 that is going to be dereferenced. And if you look at the value of R1, this is a user control value. So this is a value that is directly taken from the TCI buffer. And this is not a vulnerability per se. We don't, because we still have to look at the rest of the code to make sure that it's actually exploitable, but this is a good starting point. And finally, now that we have all the vulnerabilities that we want, we wanted to exploit the vulnerabilities. And to do that, well, you have to use the native library of native API that's available in the normal world to communicate with the secure world. The issue is that we need to write our exploit in C. And we didn't want to do that because we prefer Python. And so we have developed Python binding for the API found in the secure world. And so we have the API that is called MC clients. Our bindings are called PIM MC clients. And it provides different utilities, just xdom, disassemble, assemble, and also a command interpreter. But the most interesting feature is, it's not actually a feature, but the result is that the scripts that we are using are really simple. So here it's a script example that is going to load the trustlet, send a command to it, wait for the notification, and display the results. And it's not even 20 lines of Python, and the equivalent in C would be about 100 lines. All right, so these are the different tools that we have developed. Now let's take a look at 3 vulnerabilities that we have found and how we have exploited them. So the target here is going to be a Samsung Galaxy S7 that is running Android 7. So this is pretty old, but all the tools, all the methodology, everything I'm explaining here will still work on the Samsung Galaxy S9 on its latest version. So the main goal here is to obtain code execution in EL3. And the prerequisites are to be part of the radio group, because this is the least privileged group that is able to communicate with the TrustZone, and also to be able to write files somewhere on the device. So our attack plan here is to go from the normal world, try to find a vulnerability in a trusted application, exploit it, find a vulnerability in a secure driver, exploit it again, and then we're going to attack the trusted OS and the monitor. So the software modification that you found in TrustZone, or mostly the lack thereof, there is at least the extent bit, but other than that, you don't find a lot of mitigation. So you have no ASLR, you have no PI executables. It's possible to have canaries implemented, but we haven't really seen them on the S6, S7, and S8, and it's starting to be used a lot more on the S9, but before that, not that much. So that means that if you have a vulnerability, it's going to be pretty simple to exploit it. All right, so the first thing what we're going to do is to find vulnerability in a trusted application. So the vulnerability that we have found is in the trusted that is called SEM. So we have no idea what this trusted does. The only thing that we know is that it has a command, a buffer overflow in the 5th command handler. And this buffer overflow is due to a memcopy with a user control size, a user control source, and it's going to copy it directly into the stack. So we have a textbook buffer overflow. Now, we are able, if we exploit this vulnerability, we are able to execute code in SEL0, and now we are able to communicate with secret drivers. We are also able to make some syscalls, but the syscalls that are available to trusted applications are not that useful, and we haven't found anything interesting in them. So our next target will be secret drivers. So the vulnerability that we have found is also, again, a buffer overflow in the validator secret driver. Again, we have no idea what this driver does, but there's a buffer overflow in the 15th command handler, and it's the same vulnerability as before. So we have a user control size, user control source, and it copies it directly into the stack. So now we have, if we exploit this vulnerability, we have code execution in SEL0, but with higher privileges. And now we're able to communicate with RTM, but also we have access to more syscalls. And this is really interesting because the syscalls that we have access to are perform really sensitive operations. For example, we are able to map physical memory, we're able to create threads, we are able to make SMCs. So really interesting stuff. Right now, our next target will be the trusted OS and the monitor. So as I said, we're going to use a syscall to exploit that, and the syscall we are going to use is mmap. Mmap can be used to map the physical memory in secure and non-secure states. And the vulnerability is that there is no restriction on what you can map with mmap. And so the monitor is going to be mapped at the address 2022,000. So we map it into our secret driver. We modify it to hijack the SMC, and then we just execute the SMC from the secret driver. And this vulnerability has been patched in the newest version of Samsung's TrustZone, in KiniBee, by using a blacklist. So now you cannot just map anything you want. But with this vulnerability on all the devices, what you can do is to have code execution in EL3. And here's a quick example. I'm executing the exploit right here. Looking at the value in current EL, so the current exception level, and it's going to return the value C. But since current EL has its value shifted by 2 bits, what we do is that we shift it back on the right by 2 bits, and we obtain 3, meaning that we have code execution in EL3, so we have pretty much compromised the entire system. So now, these are the vulnerabilities. Now, what can we do fun with it? Well, the first thing we did is to develop a framework that would allow us to exploit the vulnerabilities more easily, and also to create tools based on this framework. And I'm not going to go into the details here, but the idea is that actually, I'm going to go into details. So right now, we're going to use the EL3 vulnerability to have arbitrary access to KiniBee. So what it means that in EL3, we're going to take the physical address of KiniBee, map it into the page table, flush the MMU, and now we can access KiniBee from the EL3. And from there, we are able to add a DR API function and a SVC to execute code in SEL1 natively. So at the end, with this framework, what we are able to do is to read and write memory arbitrarily, and also to execute code in SEL1 and EL3 pretty easily. All right, so the first demo I'm going to talk about is finding the master key in the monitor. So the master key is used in cryptographic operations. To find it, you can reverse. What I did is that I reverse engineered the crypto driver, that's called DR crypto. You can find this secret driver embedded directly inside KNB. And when it's doing cryptographic operation, this driver will make a call to DR API 0x1030. So you don't know the exact name, but this DR API can take 4 possible command ideas. So 0xAA, AB, AC, and AD. The one that is interesting here, and the one that can give us the master key, is 0xAB. And this DR API will make a call. We'll make a call to SVC, and this SVC is actually a wrapper around the SMC 0xB20005. And so right now we have 2 ways to retrieve the master key. So we can either directly call this DR API 0x1030 with the correct arguments, or we can directly read the value in EL3. And I'm going to do both here. But first, let's take a look at the actual function. So what is interesting here, the only thing that is important right here is that here you have the comparison with the value AB, meaning that you're going to go in this basic block, and in this basic block you have a SMC call to the 0xB2005 SMC. And if we go to the handler of this SMC, you have so you just have to follow along with the different arguments, etc. But the really important part here is that in this basic block, you have the value, you have 0x10 bytes that are going to be extracted from the address 0x10-1E4000. And this is where the master key is actually stored. And so what we can do is to read it using our framework. So here I'm just loading a vulnerable driver to make the exploit work. And then I exploit the actual vulnerability. And here I'm going to retrieve the master key using the DR API. So this is to make sure that I'm actually retrieving the correct value afterwards. So it's 98, 5F, etc. And if you read directly this value in EL3, so at the address 0x10-1E4000, we can see right here that we have retrieved the exact same value, meaning that we can have access to anything we want in EL3. All right, so the second demonstration is going to be to bypass signature checks. One of the interesting things that we wanted to do is to be able to load our own trusted applications, our own secret drivers, because it's really useful when you want to execute arbitrary code in the secret world. But to do that, we needed to be able to load this trusted because we didn't have trustonic private keys, so we were not able to sign them correctly. But since we have all the capabilities we want in the secret world, we can do anything we want, then we can just bypass these checks. So trusted applications and secret drivers are going to be loaded by RTM. And the signature is verified using TLAPI signature verified. And there are only 2 calls to this function in RTM. These are the calls. It's not really important. But the idea is that we're going to patch the instructions that are checking the value returned by this function. And here I'm going to try to load, so again, I'm doing the vulnerable driver, and then I'm trying to load a fake trustlet, so a trustlet I've made from scratch. And if I try to load it, it's going to say error, invalid operation, which is normal. But now I'm going to exploit the vulnerability and bypass these checks. And now if I try to reload this fake trustlet again, now it's going to work. And we are able to load our own trusted application in the secret world. And here you can see that we have different logs that are printed, etc., meaning that it works. All right, so the last demonstration I wanted to show you is an instrumentation of the trusted OS. So this is a really important result for us to be able to do that, because at this point we have no debugging capabilities. Everything what we have done, it was done statically or using the emulator. But by using our framework, we were able to develop a debugger, or at least some kind of debugger, because we cannot put actual breakpoints on instructions, otherwise it's going to trigger the watchdog and the phone will reboot. So what we do is that we instrument the trusted OS by replacing the instruction that we want to instrument by an undefined instruction. And then we hijack the exception, the undefined instruction exception handler, where we're going to write our own code. And what's going to happen is that when the trusted OS executes our undefined instruction, it's going to trigger the undefined instruction exception and then run our own code. And for the moment, the code that we are running in this handler is to save the current context of the CPU. And then we just execute the instruction that we have replaced, and the system just executes normally after that. So here are the results. I'm going to connect to the phone. I'm launching my debugger. And so the debugger is just a simple Python prompt. So the first thing I'm going to do is to add a breakpoint in mmap. So this is arbitrary. I just taken an SVC, and I've put a breakpoint inside it. And if I disassemble the instructions at this address, you can see that we have the UDF with 0. So this is our undefined instruction. The value afterwards, you can put pretty much anything you want, but personally, I'm using it to encode the number of the breakpoints. And right now, I'm going to make a call to this SVC, so from the debugger. And I don't know if you can see it, but the argument of the debugger is going to be the number of the syscall. So this is 7 for mmap. Then you have the permissions of the page you want to map. Then you have the starting address in the virtual address space, so the address space of the debugger, where you want to map your physical memory, the end virtual address, and finally your physical address that you want to map. And in that case, it's going to be the first page of the secure monitor. And so I've executed my syscall, and now if I display the logs of the debugger, so I've stripped the rest of the results. There are more calls to the SVC that are made between the starting of the debugger and my own call to mmap. But here is the result of my own call, and you can see that I have access to the state of the CPU. And here you have R1, which is 0x100,000, so my start virtual address. In R2, I have 0x101,000, my end virtual address. In R3, I have my permissions. And in R4, I have the physical address that I wanted to map. And so this is really interesting to us, because now we are able to debug the trusted OS, and it would be really useful to find other vulnerabilities in Samsung's TrustZone. All right, so that's it for me. Thanks very much.